So I'm very delighted to have the Professor Rameshwer Adhikari with us, and with a short brief of Adhikari, sir, I will request here to present his talk. Let me narrate his details. Dr. Rameshwer Adhikari is Professor of Chemistry, Central Department of Chemistry, Jhabua University. Currently working in Research Center for Applied Science and Technology, Recast TU. He also served as Executive Director at Recast from 2017 to 2020 and a visiting professor at Rouen University, France. He also served as visiting faculty at Mahatma Gandhi University, India, also to the Toyota Institute of Technology, Japan. He serves currently as adjunct professor at Indian Institute of Technology, Guwahati, and SRM Institute of Science and Technology, Tamil Nadu, India. Dr. Adhikari has been passionately working in promoting and mobilizing young scientist activities in the country for the last 17 years. Dr. Adhikari studied chemistry in Tribhuvan University, Kathmandu, and then graduated from Martin Luther University, Halle-Wittenberg, Germany in 2001. He is a fellow of International Union of Pure and Applied Chemistry and recipient of Alexander von Humboldt Fellowship, and also serves as Ambassador Scientist of the AVH Foundation from 12 to 2016. He is recipient of POLYMER International Material Science Prize and Technology Award of Nepal Academy of Science and Technology. Dr. Adhikari is currently a scientific committee member of POLYMER, International Polymer Characterization Forum, steering committee member of Asian Pacific Conference of Young Scientists, life member of Nepal Chemical Society, and founder president of Nepal Polymer Institute, NPI. He has co-authored and authored more than 220 research papers in peer-reviewed journals, books. He guided PhD research scholars, where 20 already been completed and 10 are in running. And he has guided more than 120 master's and bachelor's projects. His research area includes polymer, biomaterials, nanotechnology, and natural products. With this short introduction, I request Dr. Adhikari to please continue with his talk. Thank you, sir. Thank you very much with us.
Thank you, sir. Thank you, Professor Saxena Amitji, for very kind invitation and for very kind introduction. I am very much honored to be the speaker in this very nice workshop. Also, some of the lectures I could enjoy. So thank you so much for the invitation. And in my presentation, as I informed, I'll be talking about polymer characterization by microscopic techniques. So you can see the content of my presentation. So first of all, I will talk briefly about the history of microscopic techniques, very briefly. Then I will go with the help of some examples on polymer and polymer nanocomposites, the application of transmission and scanning electron microscopy. So very welcome everybody who is listening to me. So if you have any question, you can ask me anytime or at the end of my presentation, or you can also write me an email. I will be very much happy to also to collaborate with the faculty members who are over here, also with the graduate students and other students. So if we go to the history of microscopy, we see that the history goes back to the invention of the glasses, because the glasses are very fundamental to the discovery of microscopy. So it happened very, very long ago, as you can see here, but it took about more than 1,500 years. The first microscope was made by the Dutch scientist. So later, in the 17th century, Antonie van Leeuwenhoek improved the single lens microscope, and he could revolutionize the microscopy world by analyzing many microorganisms that we have studied in our schools. Later in the 17th century, as most of us all know, that Robert Hooke made improvement in the optical microscope, light microscopes. And over 2 centuries, optical microscopy kept on revolutionizing the biological science. Most of the knowledge about the structure of cells, microorganisms, and so on that we have today is from this era. But in 19th century, Ernest Abbe was able to show that, or he showed that the magnification of the optical microscope is unfortunately limited. The things that are smaller than the wavelength of the light are not visible, cannot be made visible by the optical microscope. And that was the best for the invention of electron microscope, the first of which was made in 1931 by Ruska and Knoll. Among them, one of the person was still alive in 1908, and he could get Nobel Prize for that after more than 50 years. Then in 1980s, scanning tunneling microscope, scanning force microscope or atomic force microscopes were invented. So this is just an example of the first electron microscope that was made in 1931, and it was the replica by Ernst Ruska that is found in the Deutsches Museum in Munich in Germany. So these are the people. And later on, Binnig and Rohrer, as I mentioned, got Nobel Prize in 1980s, I think it is 1986 or 84, for the discovery of scanning tunneling microscope, with the help of which they wrote, of course, the name of their company, IBM, in which they were working at that time. So this is, as most of us know, the scanning tunneling micrograph of almost atom by atom on nickel single crystal, and it was also published. So this is what I was talking to you. Ernst Ruska, who was one of the young people at their lab in 1930s, Ernst Ruska shared the Nobel Prize with Binnig and Rohrer in 1986 for the discovery of the electron microscope, which was done, of course, in 1931. So before going to the main part of my presentation, let me show you some of the pictures for motivating you why we need electron microscope. So we have perhaps sometimes asked ourselves why these cells are so strong. So these are found everywhere. And the reason behind is, if we have a look on it, with the help of electron microscope, we find that these cells, this is particularly of the nacre cells, these cells are made up of layered structures, the microstructures, the calcium carbonate layers embedded between the protein layers. So you can always have a look on the scale bar. This is what we have to do when we are looking at the micrographs. So this is the reason why these materials are so strong, so durable, and the animals do not get wet when they are in water. So this is water lily. We all know that lily or the lotus, the leaves do not get wet in water, and the surfaces are hydrophobic, so that the balls of water may be formed on the surface. And the reason behind it can also be found by studying the surface of these materials by the electron micrograph. These are the scanning electron micrograph of the lily surfaces, or a lily-like surface, that the higher magnification, this scale is 1 micrometer, and we can see that these are the common nanostructures of different shapes that are found on the surface, and that make the material, the surface of the material, so hydrophobic. So I don't want to elaborate on it. I just want to stop here and go to my presentation, main presentation. So let me start with transmission electron microscope. Let us start with the basics of electron optics and light optics. We all have studied in high schools about compound microscope, the principle of compound microscope. We have studied that in the compound microscope, we have a light source. Then for these light source, the light from this source, for condensing it, we have a condenser lens. And this condenser lens aligns the light coming from the source to the object, tiny object. And this object is magnified by objective lens to an image B. And this intermediate image becomes, for projector lens, the object, and the magnified image of B, which is actually the much highly magnified image of the object A, is image C. So what we see basically is that, I don't want to elaborate the principle. What we see is there is a combination of different kind of lenses, condenser lens, objective lens, and projector lens. The main function of condenser lens is to align the light from the source to the object, which is imaged by objective lens. And this makes the first image, intermediate image, which is much more magnified by projector lens. And the similar principle works in case of the electron microscope. This is very simple diagram. Only the objects put here in another. In the same way, so we have then have the image objective lens, and which is much lens, and we have the final image. The principle is more or less exactly the same. The only difference is that we have to work the whole thing, we have to put the whole thing in vacuum, because which may interact with any objects, anything, any kind of particles on its way. So in order to avoid that and to make its interaction only with the object, so we have to put the whole thing in vacuum, the first thing. And the second thing is that the lenses are, of course, made by not the glasses, but they are made by the magnetic fields. So in this situation, what we have is the very high magnification of the object. This can be explained by this equation, which we derived from de-Broglie equation, which is shown here. Starting from this de-Broglie equation, we can reach to this equation, in which if we apply an acceleration voltage of 150 kilovolt, 100 kilovolt, up to 100 kilovolt, then we will get the wavelength, the lambda value, which is much more less than few nanometers. So this means that by applying quite a high amount of voltage, acceleration voltage to the electrons, we can achieve the wavelength of much smaller value than that of the light, which is in the range of few angstrom. And with this help, we can image the objects which are as small as few angstrom in dimension. So this is the main principle. So now let us try to apply this principle for the objects. How we can image the materials and the powers with the help of electrons in transmission electron micrograph. So what we have seen is basically the contrast that we see in transmission electron micrograph is based basically on mass and the thickness. That is, I want to explain here in some detail how the images are formed and contrast is formed in the images. So let us say we have an object which has different as presented here, thickness D1 and the thickness D2. D2 is of course higher than D1. And this is the sample thickness. And then rho 1 is the lower density, and rho 2 is the higher density. So if we have electrons which pass through the thinner substances, and here the same electrons pass through the thicker objects. So we can imagine that when the electrons are allowed to pass through the thinner objects, most of them will pass through. While if the electrons pass through the thicker objects, many of them will be scattered. And in this case, if we allow the electron pass through the same thickness, but with much higher density, then the electrons will be much more scattered, and the electrons reaching the another part unhindered will be much less. Whereas if the density is higher, but is lower, then as expected, the number of the electrons is scattered will be low. So exactly this effect will be analyzed in forming the images in transmission electron micrographs. So for example, just have a look on this electron micrograph. This is the transmission electron micrograph. The scale bar is also shown. The bright area, these areas, for example, this is the area where the amount of scattering is very low. This situation. And if we have here the particles which have higher densities, in this case, the gold nanoparticles, inorganic particles, which scatter more electrons, and they become darker here. And in this situation, as depicted here, we have the polystyrene particle, organic particle. The density of the organic particle is, of course, very low, but still it contributes significantly in the thickness of the substance. Therefore, because the higher thickness of this region, this area appears much darker area. This is the thicker area, and these particles are the denser particles inside the thicker areas. So in this case, we can see that if we have the idea of the density of the materials in the heterogeneous substances, then we can estimate how the substances are imaged in transmission electron micrograph. So I want to show you some more examples to illustrate how the images are formed and how we can interpret them. For example, in this picture, I'm going to present the nanocomposites of polymer. In the left case, nylon, polyamide, composites with layered silicate. So if the thickness is the same, we can imagine that nylon, which is made up of organic material, carbon, hydrogen, sometimes nitrogen, has much less density than the layered silicate, which has silica. So therefore, these layer structures, the brighter area, darker areas, darker lines, this is the area of the layered silicate having the higher densities, which is able to scatter more and more electrons. And the brighter areas here, this is occupied by nylon. In the same way, in the right images, you can also have a look in the scale bar. This scale means this length is 200 nanometer. The brighter areas is the relatively low scattering plexiglass, PMMA, polymethyl methacrylate polymer, and the darker areas represents, of course, the silica, because by virtue of their higher densities and their ability to scatter more and more electrons. Knowing this, we can still have some more ideas about this picture. This is the transmission electron micrograph of another kind of nanocomposite, the bone. Bone is a kind of composite material comprising high amount of hydroxyapatite mineral embedded in the matrix of collagen. So we can therefore imagine, I'm sure you have been already thinking of which could be the hydroxyapatite and which could be the areas occupied by the collagen. In this image, the darker areas, this area, the platelet-like area, these areas, which are like plates. This is the areas occupied by hydroxyapatite platelets. And these appear darker by virtue of their higher densities and their ability to scatter more and more electrons. And the brighter areas, like this, or like this, these are the areas occupied by the polymer, the collagen, the biopolymer. So in order to image these small structures by transmission electron microscopy, how the samples are prepared, how thick should be the samples, how they are prepared. In order to explain this, I want to show you some of the slides to illustrate the sample preparation for transmission electron microscopy. So already mentioned, there are some basic requirements for transmission electron microscopy specimens. The first is there should be complete lack of water or any other volatile components in order to avoid any kind of contaminations. Otherwise, we are targeting at getting the information from the sample surfaces or the specimens. If there is any contamination, then the information will be contaminated with the contaminants. Then these specimens should be able to be stable under high vacuum conditions, because the electron microscope system is put in high vacuum condition. At the same time, these sections, the samples, the specimen should be stable against electron beam damage. There should not be any thermal stress, neither there should be any physical stress. As in any kind of electron microscopy, for the electron microscope, there should be regions of electron opacity, or the areas in which the electrons are scattered, partly or completely. There should be areas where the electrons pass through, electron transparent. Otherwise, we will not get any contrast. And also the size of the specimens, not only about the thickness, but thickness should be very small, yeah, of course. The size of the specimen is also very important. If you can, I mean the length and the breadth, or if the circular specimen is there, the diameter, that should be very small too. So for this, the sample preparation is, there are many methods for sample preparation. The very common method is so-called solution casting. So solution casting is you have the polymer, you find a suitable solvent. With the help of suitable solvent, you make a mixture of polymer and the solvent, pure solvent. We have the solution that could be of different concentration, but generally we use low concentration of the solution. And we can utilize so-called deep coating method. Deep coating is taking the substrate, clean and very flat surface to the solution and dipping it into the solution and taking it out with a given speed, particular speed, deep coating. And spin coating is, of course, putting the solution onto a rotating disc and spinning the disc with some speed, given speed. So that is called spin coating. And this is very, very popular technique for preparing thin film for transmission electron microscopy. So the samples can also be prepared by spraying the solution of suspension onto the grid, the specimen holder for the TEM, that is so-called grid directly, that can be sprayed. Or we can also make so-called ion beam milling or shadowing. However, if we are interested in the bulk material properties, how the sample looks inside, how are the structures, are they nanostructures, microstructures? So if you are familiar with crystalline polymers, how the crystals look like, how are the spherulites, how big are they, what is their orientation, and so on. In that case, what we need to do is we have to take the sample and we have to section them, we have to coat them. So that is called ultramicrotomy. Microtomy is therefore the technique by which we can make the sections. And if the sections are very, very thin, if it works in ultra scale, then the microtomy is called ultramicrotomy. So what do we need? Therefore, we need microtome or ultramicrotome. Of course, for sectioning, we need very sharp knife. This sharp knife may be made of glass, can also be made of metals, but for transmission electron microscope, this is not enough. Glass knife would be okay. Or the best knives are made from diamond. Then we with the help of that microtome and sharp knife, we can prepare well-prepared specimen, which of course need patience. I will tell you why we need patience. Patience is needed everywhere, in every case in life, but in preparation of sections for transmission electron microscopy, the patience is really very, very important. So why we need patience? Because generally we are utilizing very expensive, fragile substances. These are the, I don't know why, I'm not going to make any advertisement of the companies, but these are the companies, Diatom and so on. They prepare very good knives. So this is a kind of pan where we can, and for example, here also, where we can put water or any floating liquids. And this is the diamond knife. For example, here also, and this here also. The length of this knife is few millimeters. Okay, so what we do is, when we are taking this knife, this is the sample, we cut them in like a pyramid. Then we cut the sections with the help of eyelash, a device or tool made of eyelash. We align them, we take them, we pick them and put it into the sample holder. And if the sample specimen is not reactive with water, if it does not damage water, does not damage the sample, then what we can do is we can make them float onto water, and this band of the sections that is floating onto the water can be picked with the help of the grid and with some tools, and we can put them into the microscope. And for the polymers, typically, the thickness of this section is about 50 nanometer, can be 40, or can also be 60 nanometer. So 40 or 60 nanometer is, what is this thickness? How thick are 50 nanometers? Just to imagine that, I just want to tell you, I don't have much hair. If you have hair, you can just think about it. The hair is, the thickness of the hair is about, some people have thicker, some people have thinner, but generally the thickness of the hair is about 40 to 50 micrometer. So if we imagine that 50 micrometer thickness of the hair. It means 50,000 nanometers. Okay. So if we take the one here, and if we make vertical sections 1,000 times, one of the sections will be 50 nanometer. So that is the extent of thickness of the samples that we need for transmission electron microscope. Of course, as I said you in the beginning, the requirement on the thickness of the substance depends also on the voltage, acceleration voltage you are using in the electron microscope. If the thickness is high, then you need to utilize higher amount of the voltage. But the danger, the risk of the damage of the specimen is also increases with the voltage, acceleration voltage. So much about the sectioning. And many of the polymers like rubbers, thermoplastics, and so on, they are soft. And we have the difficulty in sectioning them. You know why? It is like sectioning of the cheese, If you have butter, if you have cheese, and you want to make, with the help of your knife, to make thin sections, it is like, also making the sections of the bread. If you want to make them uniform thickness, we have the difficulties because this is too soft. Even if we are able to make the sections, then the sections are squeezed due to the mechanical force that we apply. So how to get the uniformly thick specimens of the polymers, of the soft polymers? If you have the hard polymers like polystyrene, PMMA, it's okay. You can do that in the room temperature. Room temperature is also sometimes different, Yeah. Some time ago, I read that the thick temperature in room temperature in Kerala was 46 degrees Celsius, in which some of the polymers becomes very soft. Anyway, in that case, what we have to do is we have to think of cooling the sample so that the sample becomes glass or glass-like. And in that case, we have to cool the sample below the glass transition temperature, so-called TG of the polymer. That we do. And we do cryo sectioning. We do the sectioning that we did not at room temperature, but at lower temperature. Of course, we have to devise the microtome, ultramicrotome in the similar way. And the next thing is either the bulk specimen or the thin film can be strained, because staining is important, If we have polymer, for example, polypropylene, we have, what do we have in polypropylene? We have carbon and hydrogen. In polyethylene, also carbon and hydrogen. So if you have a mixture of polyethylene and polypropylene, you have only carbon and hydrogen. And these are very low atomic number, atomic mass elements, no contrast. So in order to make, by staining, it is difficult to stain only carbon and only hydrogen. Not possible. In my knowledge, it is not. It's not possible today. I don't want to say impossible. Today, it's not possible. But for electron microscope. But if you have polypropylene and polyethylene, by virtue of their high molecular weight, they do not mix. The entropy contribution is too low. In that case, they segregate. Even in that case, it is difficult to image them separately, because there is the contrast between polyethylene and polypropylene is very, very low, because the density of polypropylene and polyethylene is not very different. So we have to do some staining, as in the optical microscopy, as in the compound microscope, in the school compound microscope. And of course, in that case, we have to think about staining time, staining agent, and so on. I don't want to elaborate, but the very common staining agent for scanning, transmission electron microscopy are ruthenium tetroxide and osmium tetroxide. vapors, both of them are highly toxic. So this is the overview of the staining agent that are used, which not only stain the structures, but also do fix the structures of the polymers. Without elaborating it, I want to go directly to some examples. So if you are listening to me, thank you so much. I hope it is not getting so bored to you. I want to show you some very nice examples of transmission electron microscopy of polymers. This is an example of the transmission electron micrograph of a mixture of density polyethylene and very low density polyethylene. I don't want to elaborate why they are so called, but particularly, mainly, high density polyethylenes have much linear structures in the chain. And very low density polyethylene or low density polyethylenes have some branched structures that makes a kind of hindrance in the crystallization behavior. Therefore, high density polyethylene is more crystalline, very low density polyethylene is very less crystalline. Therefore, the polymers are generally called semi-crystalline, even if they are crystalline. Anyway, so you can see in this micrograph some brighter areas and some darker areas. What are these areas? The question comes. I'm sure you have been already thinking like, okay, this should be polyethylene and this should be very low density polyethylene. Without giving you any surprise, I will tell you these areas, the darker areas, because these are polyethylenes, made of only carbon and hydrogen. No possibility of imaging them about their segregation, about their structures without staining. So this material was stained with ruthenium tetroxide. Okay, and staining agent, where does the staining agent go? Like in the staining of the sections of biological samples of the cells that we did in the schools. Where does the staining agent go? That goes to that areas where is the structures are loosely bound, or if there is some kind of empty space, isn't it? The very low density polyethylene is, of course, low density. It allows more staining agent to go into it. Therefore, the staining agent is there, which is ruthenium tetroxide, that increases the density of the section. Therefore, the darker areas are the staining agent ruthenium tetroxide rich areas. Therefore, they scatter more electrons and appear dark in the transmission electron micrograph. In contrast, the brighter areas, this should be therefore high density polyethylene. If you look at this also carefully, you will see that these brighter areas also constitute some much brighter areas and some less brighter areas. The brightest areas are those which don't allow the staining agent to go into it, and that are the crystals. And those areas, so which, for example, here, which appear relatively brighter, but not as bright as these layered structures, so-called lamella. And this is the amorphous region, which allow a part of the staining agent to go through it. Therefore, you can see that the darkest areas are low density, very low density polyethylene. Okay, the brighter areas, high density polyethylene. The brighter layers, the brightest layers, which are also even going into the very low density areas. This is high density polyethylene crystals, so-called lamella. And the rest are the high density polyethylene amorphous regions. So let me go to another example. For example, this one. Please have a look always on the scale bar. This length is 200 nanometer. You can see here the nanostructures of polystyrene polybutadiene-based block copolymer. So this was stained, the section about 100 nanometer, 70 to 100 nanometer was stained by osmium tetroxide. Why osmium tetroxide? I don't have time to explain today. If you have interest, you can ask me anytime or later, or you can write me. But this was stained by osmium tetroxide, which has the affinity to go to the areas where there are double bonds. For example, in polybutadiene, the osmium goes to polybutadiene, and this polybutadiene therefore scatters more electrons and appear darker. So darker areas are polybutadiene, the brighter areas are polystyrene, and you can see also in the darker areas, also you can see small worm-like domains, which should be of polystyrene again. So only the skilled microscopist can prepare such samples effectively in such a way that every individual structures can be interpreted. So therefore, we need ultra skill. So this is another one, multi-layers of polycarbonate and polyethylene terephthalates. Here we have the density of polycarbonate is a little lower than that of polyethylene terephthalate. Staining agent goes therefore, of course, to polycarbonate, as you might have thinking. And in this case, the staining agent was osmium, ruthenium tetroxide. You can imagine that the darker areas where there is more ruthenium tetroxide, the staining agent appears darker, and the brighter areas are, of course, polyethylene terephthalate, PET. So maybe I don't want to elaborate much more because I think I have 10-minute time, Professor Saxena.
We have, sir. We can continue till 12:30.
Okay. So I think until now, I gave you a glimpse of application of transmission electron microscopy for characterizing the small structures, micro and nanostructures of polymers and polymer blends and composites by transmission electron microscopy. So please permit me to give a very brief introduction to scanning electron microscopy. So this session, this FDP program is, of course, dedicated to polyelectrolytes. Also, the methods of imaging the general polymers with electron microscopy is valid also for the kind of polymers we are dealing with in this symposium, in this workshop. So unlike the transmission electron microscope, there are some differences. So what we see is transmission electron microscope have the electrons that scatter when they pass through the thin section of the specimens. Some scatter more, producing darker areas. Some scatter small amount, producing brighter areas. And these transmitted electrons, which those that do not scatter, are used to produce images. And already mentioned, darker regions in the specimen scatter more electrons and appear darker, and so on. So what is about scanning electron microscope? Transmission electron microscope is one in which the electrons are transmitted. So scanning electron microscopes uses not the transmitted electrons, but the reflected electrons. So this is a kind of reflection microscopy. SEM uses electrons reflected from the specimen surface. And if we have some information about these electrons, then we can produce, with the help of those electrons, which are reflected from the specimen surface, three-dimensional image of the specimen. Very useful microscopy. And I should tell you, with a little patience, with a little interest, this microscopy is very interesting and very easy to learn, not difficult at all. Okay, very foundational information, foundation of scanning electron microscopy is shown in this picture. If we have being incident on the sample surface, then many phenomena happen. For example, X-rays are produced, OJ electrons are produced. Then we have cathodoluminescence, we have secondary electrons, we have primary backscatter electrons, and so on. And each of this information can be utilized for the analysis of the surface. So we have X-ray spectroscopy, or we can do some ESCA, electron spectroscopy for chemical analysis. Or we can do OJ spectroscopy, and so on. I don't want to go in the detail. I just want to focus on the secondary electrons and primary electrons. And they make secondary electrons. Secondary electrons give rise to secondary electron mode, which is illustrated here. So we have the electron beam, primary electron beam come into the sample atom. And when these electrons, primary electrons are coming to the sample surface, they make the sample surface atoms valence electrons or from the inside to go out. So electrons are ejected by the primary beam. And so we have secondary electrons. And these secondary electrons are utilized to analyze the sample surface. The secondary electrons have lower energy, and they are utilized to produce sample details and sample topography. So in this case, what we do is we apply the primary electrons, which produce secondary electrons. These secondary electrons are counted. They are received by the detector. And with the help of, we produce the image, secondary electrons mode. In another case, what we do is we have the primary electrons, primary beam of electrons that interact with the surface atoms. And we are interested, surface atoms and soft surface. We are interested in these, the electrons, that the primary electrons which are backscattered, the Rutherford kind of scattering, backscattered electrons. And these have the higher energy, of course. And these backscatter electrons are counted, they are analyzed, which have high energy, and they give us the information about the composition of the surface. So I will just give some examples how these modes, utilizing the backscatter electrons, BSE mode, and secondary electrons, the SE mode. How are these modes utilized to make images? Give us examples. These, how elemental composition is from BSE electron, BSE, and so on. And ask me, we can discuss later. So also for the scanning electron microscope should be generally a vacuum, and there should be no water and volatile substances. And the sample specimen should be stable against electron beam damage because we are utilizing very high energy primary electrons, which will be interacting directly with the surface, specimen surface. And the surface should be conductive, generally. If I'm not talking about all the conducting polymers that can be utilized without doing anything most of the time, but not always, because they can also be damaged. Otherwise, we have to make the sample not charging and conducting. So sample preparation can be done in different ways. I will show you the examples and you will understand why. First of all, by microtomy, if we are interested in knowing how the heterogeneous sample look like inside in the bulk, then in that case, we have to do on the microtome surface some kind of etching. We remove some materials and we have topography of the specimen. Or what we can do is we can sample. If it is soft, we can make a notch onto the sample, and then we can do nitrogen, liquid nitrogen, whose temperature is very low, and we can break it. Fracture surface produce the fracture surface, and also by producing the fractures at low temperature or even at high temperature, at room temperature. In case of heterogeneous substances, semi-crystalline or polymer blends or polymer composites, by applying the mechanical force during the fracture process, different substances in the blend or composite, in the heterogeneous substances, the different components respond in different ways with the mechanical force. And that results in different kind of surface structure in the fracture. And that can be studied by scanning electron microscope wonderfully. So, and that can be also the deformed sample from impact testing, tensile testing, compression testing, or whatever test you are doing. That can be any kind of deformed sample surface. It can also be thin surface, thin films produced by the ways how the transmission electron microscopy samples are prepared. That can also be utilized. Or you can think of making thin films, thin sample by innovating your own weights. Okay. I already mentioned that we need to make the sample surface conductive. And that we can do by spotter coating the sample surface with a thin film of gold, silver. You can also utilize platinum. That should be stable metal. Or we can utilize carbon film. The thickness of the coating should be few nanometers. And the objective of this coating is, as said, to avoid electron beam damage, making it stable, and also avoiding the charging, making the film conducting. And chemical etching can be done, which is generally performed by permanganate etching, in which we utilize the potassium permanganate together with some strong acids, mineral acids. And the purpose is to expose the internal morphology of semi-crystalline polymers, but it can also be done for other polymers, blends, and composites, not limited to semi-crystalline only. So let us come to some examples. Have a look here. So this is, I think what it is. No. This is the scanning electron micrograph. The crystal of wine. So in you to wine or alcohol, the fact that if you put wine if you store it correctly, then crystals are. So once we had this situation while we were just talking about the drink, and we took it into the microscope. So we did this test in University of Halle, Wittenberg. So what you see is, this is some kind of sodium potassium tartrate or some tartrate crystal. I don't know exactly right now. So anyway, these are crystals. You can see a layer, another layer here. Above this layer is this one, above this layer is this one, above this one is this here, and above this is this is this. And if you go to another platform, another layer, above this layer is this one, and this one, you know, the highest layer. And this is, never forget to have a look in the scale bar. What I feel sometimes when I go to the conferences, that sometimes we see that the electron micrographs are presented without giving a hint about the scale bar or about the magnification. This is very critical. This is very important. Also, in which mode the sample were examined. For example, this was a scanning electron micrograph produced in secondary electrons mode. And here, what you see is, so the contrast is here uniform, so darker areas. And also uniform, also uniform, also uniform. Nothing is there. But when you come to the edge here, or this here, edge, in the edge, you see all the time that the edges, the boundaries, they are brighter. Why are they so? Why are in secondary imaging, the boundaries, the edges of the specimen, if the thickness of the sample is the same, why they do appear brighter? There is a reason. The reason is, in simplified way, if I explain that in simplified way, the reason is that when you go from one uniform plane to another plane, then in the edge, in the boundaries, you have the area when the electron beam is falling. You have here a kind of spherical interaction volume, and here you have a kind of elliptical scattering volume. It takes more volume to interact into the specimen surface. That produces more secondary electrons, and that makes the regions appear brighter. So if we know this, very, very general picture is this. There are many other factors too. If we know this information, then we can better interpret the scanning electron micrographs. I want to show you some pictures. So this was multi-wall carbon nanotubes. So many of us are working with carbon nanotubes and nanomaterials, which are also at the same time being considered as one of the risks for the future. So I don't want to elaborate. So this is 500 nanometer, this is scale bar. So you can imagine if the samples are prepared and if we have the good microscope and if the microscope is skilled one, we can image with the scanning electron microscope very easily. This is imaged with very simple microscope, yeah, of Jewel company. These are the multi-wall carbon nanotubes. When we sputter the with gold, can also be done with silver. So this was the composite of polymer with natural fiber. In this case, particularly the bamboo fiber. So you can see that. You can see only bamboo actually. So this composite was some 40% bamboo floor and some 60% biodegradable composite. So in this case, what you see here, these are these structures where there is no this kind of structure. These layered structure, layered architecture is of course bamboo, and others, which is merely acting as a cementing material for this composite, is the polymer. And the principle, the thing with bright and dark contrast. You can see that here, where there is a age, or there are brighter things. So let me go to another example. This is the natural fiber composite with a starch. You can see that these are the holes, where perhaps these kind of fibers were before. So these elevated structures are, of course, natural fibers. This here also, what does it tell? In contrast to the previous image, this image tells us that this composite is not very compatible. You can see that the fibers are pulled off. They are separated from each other. It means it gives us the hint on the compatibility of the composites. So, SEM not only tells you what kind of structures are there, how big they are, but it also tells us about the compatibility of the substances. Another example, this is the polystyrene with boehmite nanocomposites. Boehmite. These are the particles of boehmite. This here. Highly filled polymer it was. And in that case, when the polymer was highly filled, you see the areas occupied, the volume occupied by the polymer was very small. When the brittle occupy very small volume, when they are very thin layer, they have the ability to flow like tough plastics, like flexible plastics, like polyethylene or polypropylene. And this is the result why they produce these kind of fibrillar structures on the fracture surface. So I will show you some more examples. It was the sample prepared by etching. It was polypropylene prepared by permanganic etching. Sample was sectioned, and then the bulk sample, after the sections are removed, was taken. It was treated with a mixture of sulfuric acid, orthophosphoric acid, and potassium permanganate. Of course, in water, solution was made in water. This etchant was utilized, as you can see here, the lower magnification is here, on the surface, and the etching did remove the amorphous, more loose part of the surface was removed, and the crystalline part was there. And this is the typical structure of so-called polypropylene spherulite. So if we take very brief etching on polypropylene sample surface, then we see these spherulite structures. This is the boundary between the spherulites. So this is one region which is not very well crystallized. So these are the radiating lamellar structures of polypropylene. And if we have a blend of polypropylene with much flexible polyethylene oxide, which is but not very well bound to polypropylene, they are removed by etching. So you have produced this kind of empty spaces. You see that. And if you look from the distance, you can see that the spherulite structures of polypropylene is still there. This is a polyspherulite. Another spherulite. Boundary is there. And PEO is etched away. And this is perhaps not, I don't have much more examples now. One beautiful example of imaging the polymer blend with a scanning electron microscopy in the SE mode, a second electron mode. This is a polyethylene with, if you remember before, I was talking about high density polyethylene and very low density polyethylene. Very similar substance is it. High density polyethylene with ethylene octane copolymer, which is structurally very similar to polyethylene high density, but it has many small branches. So this brighter, this is low magnification image, and this is high magnification image. Scale bar is here, scale bar is here. So this, in the higher magnification, you see this so-called lamella. You can see that some of the lamella are 500 nanometers, so 2 micrometer long. You can estimate that with the help of this scale bar. And this area, which does not show any crystalline region, is ethylene octane copolymer. We can wonderfully see that the high density polyethylene part is dispersed very nicely, uniformly in the matrix of elastomeric polyethylene polyoctane copolymer, ethylene octane copolymer. So I skip this. I just want to show one example with BSE mode, in which the coating is not done with metals. Otherwise, if you do the coating with the metals, then you will see the chemical structure of the metal. So we do that with carbon coating, and this is a rubber fracture surface. Rubber fracture surface was made, and then it was coated with carbon, and this was rubber, filled rubber, silica filled rubber. I think layered silicate filled rubber. You can see some steps-like structures here. Also some bright dots. Maybe this is some inorganic substances. So, but SE imaging does not tell us much about it. If we do image of the same area with backscatter electrons, then we have this result. You can see that the darker areas is organic polymer, and these brighter areas are the areas in which more and more scatter electrons are produced. Backscatter electrons more and more are produced by those areas which have higher atomic number, the inorganic substances. And scanning electron microscopy can also be utilized to image how the different phases are dispersed in polymer blends. This is, for example, a blend of, you can see that it could be one kind of polymer, one kind of polymer. You have already imagined what different kind. You have seen that here. This is a rubber, flat surface, nothing. Also here you see, okay, this looks like a pit, but this is defined by some mechanical deformation. But this area is very similar to what we showed before. So this is a kind of good rubber, and this one is a bad rubber, plastically deformable rubber. Rubber should not deform plastically. It should come back. It should elastically come back. Okay, I think I stop here. Also because of the time, if you have any question, I'll be happy to answer. And all the things that I brought you here is in this book, also could be found online, Electron Microscopy of Polymers. So before I finish, I just, Professor Saxena, please give me 1 more minute. I just want to, if there are some young faculty members or young students, I have a very brief story to share you. It will take 90 seconds. So this man is Dmitry Mendeleev. Dmitry was the person who wrote these letters very long ago. So this was the foundation of what we call today periodic table. So this guy is very, very famous. So this is what we have today due to his contribution. About him, I want to tell that he was born in 1834 in Siberia. As youngest child of about a dozen or more children of the family, Dmitry was little, father went blind. Later, due to some accident, our mother also lost her job. For the dozen of children, they needed a lot of money. This young boy, when he finished the school, then he wanted to go for higher studies. He was in Siberia. very far away from Moscow. Perhaps the school was also not very good at that time. And there was no train, there was no plane. Even there were plane and train, they did not have money. Then mother and the son, they decided to walk 1,000 kilometers from Siberia to Moscow. What happened? When mother and child were there, he was not qualified for admission in the university. They did give up travel another 1,000 kilometers to St. Petersburg in 1850s, where he got admission. Thank you so much for your invitation and attention. This is all I want to explain. So thank you.
Thank you, sir. Thank you very much. It was really so fabulous for us. The vision toward the microscopic studies has been now changed. Normally we go and we perform SEM and TEM and we simply bring the image, and we are more interested to put in the research papers in spite of studying in such a great detail. And I think on behalf of all the participants who joined this session, I thank you very much to be so elaborative, so descriptive about the SEM and TEM. I think most of the participants are not having such a great information detail about the SEM and TEM. So thank you very much, sir. Thank you. Thank you.
Thank you, sir. Thank you so much.
Now the session is open for all those who want to ask a question. Satish Yadav, you want to ask anything? Want to ask any query? Parish Yadav, I think your voice is not clear. If you have any query, you can post it on chat box. Anyway, I have so I'm like we are into the system of polymer materials, and we are taking the SEM and TEM for polymeric materials. Whether we can do the same studies for magnetic materials too.
Yeah, thank you, sir. Yeah, this is possible, but for magnetic material, there is a small risk, small or big, because as we all know that the lenses in the electron microscope are made of magnets. Yeah. So if we are taking the magnetic material into the microscope, there is a risk that the magnets are, the lenses are contaminated. So in order to avoid that, what we have to do is we have to fix the magnetic material that we are taking to the microscope by embedding it correctly into some substrate, and then we have to take it to the microscope. Otherwise, it is possible. We imaged like that. What we did is we used, for example, magnetite material. What we do is we take it into the epoxy resin, we embed it correctly, then we make the sections. Then in that way, the magnetic structures are fixed, and we can image it with both with ACM and TEM. Okay. Okay. Yeah, thank you, sir.
Secondly, can we have the details about the surface defects or some impurity with the help of some of them?
Excuse me, sir, I did not get.
My query is whether we can find the impurities or surface defects or structure defects with the help of SEM and TEM.
Yes, sir. Yes.
We can.
With the help of the first information that we get with both TEM and ACM is that what kind of, how big are the structures, how right. The orientation is, and if it is uniform or not, if it is crystalline or not, and how the structures are, the first thing. And second is, we can also analyze which elemental information we need. what kind of substances are there in the heterogeneous polymer. Yeah, for example, if we have some composite material comprising of some kind of inorganic substances which are really not known, with the help of SEM, by doing this in so-called EDX, we can determine that. We can make a kind of mapping, EDX mapping, and with the help of that, we can find out, okay, this area is occupied by this nanoparticle or this particle, which is made of this metal, and so on. It is possible, sir. We also can do chemical analysis.
Okay. And the last question, because in our group, there are many students who just started their PhD, or some of them are planning to do so. Like if somebody is working on polymer electrolytes or polymeric material, and they want to go with imaging process, so which one you suggest, whether he or she go for TEM or SEM?
So for the scientists who want to do electron, any kind of microscopy, thank you, sir, for this question for our young students. Yeah, I would recommend what to do is, first of all, start with the optical microscopy, because we did not talk about optical microscopy today, but optical microscopy, the light microscopy gives a lot of information. For example, right, if we have some kind of fibers, some kind of natural fibers or any kind of fibers, what the orientation is and so on, we can do easily the polarizing microscopy, and we can extract a lot of information. So first thing that the student have to do is do the optical microscopy. You get some information about it. You already know many things about it. Then later on, go both to SEM and TEM. But general idea about the microscopy is like, people think, okay, SEM is for low magnification and TEM is for high magnification. This is not true. Yeah, we can also do low magnification with TEM, and we can do high magnification with SEM. The thing is only that the way of preparing the sample. If we prepare the sample correctly, then we can go with the help of SEM, very high magnification. Of course, it depends upon what microscopy you are using. If we are doing some microscopy with some field emission gun equipped SEM, then we can do a lot of high magnification. But even with simple SEM, we can go 20,000, 30,000 times very easily. But it should be, the sample should be very flat. It should be very well prepared. That's all. So therefore, sir, all microscopy, not only SEM, TEM, but also I would recommend to see with scanning tunneling microscope or atomic force microscope. So the students should develop their passion. Yeah.
Thank you, sir. Thank you very much. I think there is no more question from the participant side, but I thank you a lot. You talk continuously for sir, 1 hour, 20 minutes.
I got here one request also. I can send you my PowerPoint slides with PDF, and if anybody is interested, you can please distribute it to the participant.
Sure, sir. Sure. I will send it to the participants.
Yeah. Yeah. Thank you. Yeah. Thank you, sir. Thank you so much. And have a nice day.
Thank
also,
you very much, sir. Thank you.
Great Professor Bhattacharya. Yeah.
Sure, sir. I will tell him morning only he told me.
Soon. Thank you.
Yeah. We are also planning to have some international conference very soon. We'll try to contact you in offline mode also.
Okay, sir. Thank you. Bye-bye, sir.
Thank you very much. Thank you very much, sir, for accepting our invitation, sir. Thank you. So now the announcement to all the participants that we'll meet again tomorrow at 11:30. We have a talk on the ion conducting we'll meet you at 11:30 tomorrow. And once again, thank you to all who's present here for a long time. Thank you very much. Thank you, Root sir, for joining regularly our session. Thank you very much.